Hello guys, welcome back to Automata and Computability. In this course, so far we have been talking about languages and expressions, and in this week we are going to talk about languages and expressions. So last week we kind of started talking about regular expressions, saw some examples, tried to get a general understanding of the topic. Today we are going to try to make things a little more official and try to describe and define the regular language and regular expressions a little bit formally. This is basically going to be a two-part theoretical lecture that deals with the definition and properties of regular expressions. Very important to solidify your concept in all of this. So let's start by recapping a couple of important things we saw last week. So first of all, the definition itself. So we had this kind of unofficial definition where we defined a regular expression as something, by something I mean an expression, that you can create using three operations: the OR operation, the concatenation operation, and the closure operation. There were two types of closures, so you can say four operations, but essentially the closures are the same thing. So anything you can create with using these three operations is a regular expression. That was our informal definition. One other important thing was, if we have a language L and some expression R, so we have a regular language L and a regular expression R, when exactly can we say that this expression represents this language? So for that, there are two conditions that has to be met. The first one is, if there is a string that match with the expression R. Well, the expression R is a pattern, right? So there will be a bunch of strings that match with that pattern. So a string like that, a string that matches with the expression R. All such strings must be members of the language L. What is a language? A language is a set of strings. So every string that matches with the expression R must be a member of the language L. And on the other hand here, if there is a member of the language L, it must match the regular expression R. If we have these two conditions met and satisfied, we can say that the expression R is a representative expression of the language L, right? If any of these two conditions is not satisfied, the expression cannot be considered as the regular expression of the language L. Alright, so let's say we have an expression here. How do we know that this expression is a regular expression? Well, we have our informal definition, and according to that, we can see that this expression does not contain anything but concatenation, OR, and closures. So according to that, yes, this is a regular expression, but we really want something a little more concrete. So our definition is going to be inductive. Just like you saw in recursion in your data structure or algorithm course, we are going to establish a couple of base statements. We are going to define those statements as true, and then define the whole class of regular expressions by building up on those statements using recursive, or you can say inductive, relationships. So here are our base statements. The first statement says that the empty set itself is a regular expression. So if the empty set is an expression, what are the strings that match with this expression? The answer is, no string in the whole wide world will match with the empty set. So the language of this set is obviously empty. There is nothing in it. The second statement says epsilon, the empty string epsilon itself is a regular expression. And we know that the only string that matches with this expression is the empty string itself. So the language of empty string will contain only the empty string. The third statement says that any symbol from an alphabet, every symbol is by definition a part of some alphabet. So any symbol is a regular expression. So if A is a symbol, then A is an expression, and the language of A is going to be just A, because no other string will match with A. A is just an example here. This could be B or Ko or Shoreo. So the idea is every symbol is a regular expression, the empty string is a regular expression, and the empty set is a regular expression. So these are our base statements. But these are obviously not enough, because we have seen much larger set of regular languages, like the language of all binary strings. We cannot define that using only these statements, right? So we need to grow. So here is how we are going to grow. This is our first inductive step. Let's say rex1 and rex2 are two regular expressions. Don't bother about what exactly these expressions are. Let's just say they are expressions that satisfy all the conditions of regular expressions we have seen so far. So if rex1 and rex2 are two regular expressions, then the inductive step says that rex1 or rex2 is a regular expression as well. Similarly, rex1 concatenate rex2 is also a regular expression. Now, rex1 is a regular expression, so it must have a language. Okay, so let's say that language is L of rex1. Similarly, rex2 has a language of its own, so that language is L of rex2. So if the language of rex1 is L of rex1 and the language of rex2 is L of rex2, then what is the language of rex1 or rex2? The answer is the unification of those two languages. Similarly, the language of this expression right here, that is the language of the concatenation, is going to be the concatenation of the original two languages. Because let's say the language of rex1 had A and B, and the language of rex2 had 0 and 1. Then if we concatenate these two languages, we will get four strings: A0, A1, B0, and B1, right? And if you notice, in each of these strings, the first part is coming from the first expression. So first part matches with this. The first part of all of these strings matches with this expression, and the last part of all these strings match with this expression. So this actually is pretty intuitive. Now, our second inductive definition is if rex is a regular expression, then its closures are regular expressions as well. So that includes positive closure and limb closure. And similarly, like before, if the language of rex is denoted by L of rex, then what is going to be the language of rex star? Well, it's going to be the limb closure of the whole language. So this is the language of rex star. And the last one here is pretty simple. If you put a couple of brackets on either side of an expression, the expression remains regular. And what happens to the language of that expression? Well, it doesn't change, because putting a bracket on either side doesn't change a language. Alright, so that is our definition out of the way, and using that definition, let's try to see why this expression is a regular expression. One of our base statements said that every symbol is a regular expression. So A and B are symbols, so according to that, we have A and B as regular expressions. If we OR them together according to the inductive steps, this is still a regular expression. Similarly, if we take a bracket on either side and then take a closure of this entire expression and then concatenate with A and then B, we still have a series of regular expressions because we did not violate anything of the definition. So that is one part of our entire expression. The second part is just a base statement because it is just epsilon, and from our base statements, epsilon is a regular expression. The third part here is basically a series of concatenation. So B, A, both are regular expressions because they are symbols, and their concatenation is going to be regular expressions as well. So we have our three subparts here, and if we OR these three parts together, what we end up by definition is another regular expression. So that is how the definition works. Now let's look at some of the special cases. Well, when you look at this expression, you don't see the familiar closure signs. So you might think this is not a regular expression, but in fact it is, because this is basically this expression written in shorthand, and this is just a series of concatenations, so there is no reason why this cannot be a regular expression. Similarly, the expression a to the power m, b to the power n, and c to the power k does not look like a regular expression. But if you look at the conditions, m and k can be anything from 0 and upwards, and n can be anything from 1 to upwards. So basically what we are saying is a and c can occur 0 or more times, and b can occur 1 or more times. That is basically the limb closure and the positive closure. So this is also a regular expression. At this point, you may have started to feel like every expression in the world is a regular expression, but of course that is not the case. So let's look at one expression which is in fact not regular. Now this expression kind of looks like the one we just saw, but there is a huge difference. In this case, both a and b have the same variable as their power. So this expression is basically telling us the number of b must be exactly double than the number of a. So there is a relationship between the number of these two symbols, and in the operators that we have seen a regular expression can have, there is no way to ensure such relationships between two symbols using those operators, which means the language this expression represents is not a regular language, and this expression is not a regular expression. So I hope by now you are kind of feeling comfortable with the definition of a regular expression. Let's look at a couple of additional operators to wrap up our lecture today. The question mark is one such operator. This question mark basically means optional or 1 or 0. So if you see a question mark next to a symbol or next to an expression, what that means is that expression or that symbol may or may not appear in that place. For example, A, B question mark C means B might be there or might not be there. So we have got ABC and AC both. One more handy tool in regular expression is expressing a lot of symbols as a class of character. For example, in some cases, you might need to use all the digits. Instead of writing 0 or 1 or 2 all the way to n, you can write it like this. So this means all the symbols from 0 to n. And this can also have a name. The underline just indicates that D, I, G, I, T are not individual symbols. Instead, together they represent a class of characters or a class of symbols. Similarly, alphabet here represents all the lowercase and uppercase letters. So that's it for today. We are going to see you very soon in the second part where we continue to talk about the properties of regular expressions. Goodbye until then.